good afternoon, everyone. Probably Kalispera already? That's what I know about. Okay, so there's been some discussions this morning about noise. So I'm going to focus my presentation on noise, all the work we've done on noise on two projects, on RefMap and also on Imafusa, with slight differences between both of those. My name is there, but there's a lot of people working on these two projects I will mention later. So the talk is about noise from drones or innovative mobility. I'm going to start with the challenges. What are the things that are different in drones compared to commercial aviation, conventional aviation? So for example, if you have a look at this diagram over here, this is basically frequency of the sound and the amplitude of the sound. And if you compare commercial aviation, the Boeing 737 or the Airbus A320 compared with two typical drones, you're going to see a significant amount of high frequency in the drones, okay? Which we humans are highly sensitive to high frequency. So highly tonal as well, so the noise they produce is highly tonal, is attracting our attention a lot, high frequencies, and also they are small vehicles. There were questions this morning about why do you need these airflows, modeling of these airflows in a city? It's because drones are small vehicles and they are going to be quite affected by the wind conditions. Not only because of the safety, but also because of the noise they are going to produce. When you have something unsteady, it's going to try to stabilize, the RPM of the different rotors are going to change, and it's going to create a significant, more noise and probably more challenging, more perceivable as well. And all of this is making things something like this. So if you compare the percentage of highly annoyed people and then you plot different vehicles, you will see that to have the same number of highly annoyed people, a drone will be 10 dBs lower than an aircraft. Even with the drone being 10 dBs lower than an aircraft, it's going to have the same amount of people annoyed than that aircraft. Okay? The other thing we know is the operating conditions are completely different. They are flying close to people. Okay? That's one thing. You have high frequency, you have less space in the atmosphere to attenuate the high frequency noise, which is a problem. The operating conditions are difficult. So for example, there has been mentioned this morning about eVTOLs, vertical takeoff and landing. Some of these vehicles just take off, then transition, forward fly, then transition again, hover and land. So all this transition is quite complex in the sound generated. The aerodynamics is going to be really difficult, but the sound is going to be really difficult. And again, every time we have something complex from an aerodynamic point of view, you're going to have more noise, basically. Okay? So increase in tonal noise, all the things we don't want to happen, basically. The other thing we know is that the methods we have for commercial aviation compared to drones are completely different. So commercial aviation, they have a procedure for certification for noise. They measure three fixed points as they take off on land, and that's what we use. Simple measurements. In this case, you need something more sophisticated. We rely on what is called noise hemispheres. So the way we work here with drones, which is taken from EASA NORA 2 model, which is for rotorcraft, is that you measure the noise on the ground and then back propagate to the source, and then you define an hemisphere around that source. It used to be for helicopters. Now we are trying to use the same thing for drones. That is quite complex. It requires specialized equipment and expertise because you will have to have a microphone array. So for example, EASA at the moment is publishing guidelines for measurements of drone noise using one single microphone. Yeah. Okay, for the certification. If we want to have the whole picture and do the appropriate modeling, you will need at least 10 microphones on the ground. okay, which is adding complexity. You need to capture the amplitude, you need to capture the frequency, and you need to capture the directionality, so where the noise is coming from. An aircraft is very, very simple from an acoustic point of view as a whole. A drone is much more difficult. In Europe, you need everything you do in Europe has to be aligned with EASA and the EASA NORA 2 model, requiring these noise hemispheres. Again, challenges, complex field measurements, and also the noise predictions. There are no models available specifically optimized for drones. Okay? So those are challenges. So I'm going to talk about the things we do at Salford, at my university, University of Salford in Manchester, in the UK. So we've been working on developing this innovative air mobility noise framework. There's a lot of things here. Part of these things are transferred to RefMap or Imafusa, but our effort is much bigger. So what we do at Salford is, in my group, so we define a series of inputs. For example, you can define a given engine design or of a given vehicle. What are the operating conditions of that vehicle? What are the environmental conditions, wind, temperatures, etc., which are relevant for sound propagation and also for emission. Then we can work in two different streams, so we can use predictions using computational acoustics, computational fluid dynamics, basically, even analytical models. Someone mentioned low fidelity models, I think in Colossus. Low fidelity models are better to explore design space, for example, and then you can go higher fidelity. Or we can take experimental data from anechoic wind tunnels or anechoic chambers. Once we have this information, we have a process where we manipulate the sources, and then we define our sources. This is a way of, putting together these noise hemispheres with all the information. We do a bit of a spectral analysis to extract the tonal noise, the deterministic, and the random noise, tonal or ripple noise, and then we propagate this from the source to a receiver. So when you do a measurement at, say, 10 meters high, but then you want to simulate what would be the noise at 20 meters or 100 meters, or not just beneath the drone, you want to measure elevation angle of 60 degrees or something, we can do that thing. We generate the sounds, and here is when we expose those sounds to people. We ask people to rate the sounds, and then we develop our models, which is what we are doing in RefMap. So here are some of the pictures of our labs. So we can go from the physics, the actual measurement of the source in an anechoic chamber. So we have a microphone array, we have the test article in the center, then we can measure the noise at different emission angles. And then also we have state-of-the-art rooms where we can present sound in a very immersive and accurate way. And also, as part of RefMap, we are using virtual reality techniques as well to increase immersiveness and realism of the scenarios we are testing. Specifically about RefMap, what is our role there? So there's a lot of things here. So Salford is here in this area, but let me give you a bit of context. So we have, I've seen you see this morning, user input. So what the user needs. So okay, I have this drone flying this trajectory, etc. in this area. So we have agent fly with the flight dynamics simulator. There was Milan showed some pictures this morning. We have people in Delft doing airflow simulations. So these airflow simulations would be used in this flight dynamics simulator. Then Delft, another group in Delft, is taking this flight dynamics simulator, the position, the velocity, the RPM of the rotors, to make acoustic predictions. So we want to calculate from these operating conditions what the noise would be. And then Delft is integrating with us, so we just take this source, propagate propagate to the ground, and then we estimate what is the annoyance of that drone flying over. Okay? And then we have a decision making. So, do you want to fly this way, that way? Do you want to fly this particular operation, this particular route? which is coming to answer this noise-aware route planning. So things that are novel, that we are going beyond state-of-the-art in RefMap. So NASA, we have a strong collaboration with NASA. NASA developed a metric to estimate when the drone is going to be detected. So basically, if you have information about the drone, you have information about where the drone is flying. Milan mentioned this morning ambient sounds. So let's say you have a noise map of this area in Athens, and then you want to simulate, the noise from a drone flying from that way to that way. Basically, what you're going to compare is the noise from the drone only with the noise of the area. So you can do this comparison, and then you can make an estimation of the detectability of the drone. And from the detectability, our models are able to estimate the annoyance, the change in annoyance. So again, if we know the annoyance in this area is 5 out of 10, when we introduce a drone, we can estimate that the annoyance is going to increase to 6 or to 7 or it's going to be 5 again. Okay. So our models are taking this into account. So we have developed models for RefMap, taking into account what is the prominence of the drone over the ambient noise, and then a bit of information about the source, the drone, so the content of high frequency, the tonality, so how much tonal noise there are, interaction between the tonality and sharpness, or high frequency, so accounting for the tonal noise in the high frequency region, and then the number of events. And we can predict two things. Changes in mean annoyance, and we can predict the percentage of highly annoyed people. And this is very important from a decision making, because you can predict an absolute value of percentage of highly annoyed people, which is the annoyance of the area plus the annoyance of the drone. You can do that, and you can minimize that absolute value of annoyance, or you can say, okay, I'm going to estimate the change in annoyance, and you might want to optimize to reduce the change of annoyance, and maybe you might find contrary results there, because it's either you have an area, a noisy area, which is already quite a lot of people highly annoyed. You might not want to fly more drones there. On the other side, you might have a very quiet area. If you fly a drone there, there's going to be an increase in noise annoyance. So you might want to select what you want to do. Not for us, we are just developing the models for the decision maker to make a decision. Final thing, 2 slides, I'm finishing now. As part of IMAFUSA, in IMAFUSA, we've been using all the information, all the data models from RefMap to validate in the field and improve an assessment framework we are developing. So here in Athens, last year in May, I think, we did a first flight demonstrations where we brought together over 100 people. We tested a drone, a small one, Mavic 3, 1 kilogram. We flew different directions, 3 different altitudes in 2 different areas, one more affected by traffic, one more quieter. We measured different takeoff, flyovers, and landing operations, and then this was really useful for us to validate validate our models in the lab with actual people in a realistic operation. And all of this information now is part of the IMAFUSA framework, assessment framework for noise. This is quite comprehensive, so you can get quite a lot of information about noise from drones in this tool. So you can select a number of metrics, probably all metrics for aircraft noise you can imagine. They are calculated here. You can get spectrograms with frequency, amplitude, etc. You can get time series. You can get estimations of noise annoyance using state-of-the-art models, including this one from NASA. You can even calculate the aircraft noise certification metric, EPNL. And something really important as well is that you can estimate for a given drone you can estimate what's going to be the percentage of highly annoyed people for that one, which is what we use in environmental noise for decision making. Okay? And I think that's all. Thank you.